Good morning, welcome to new lecture. Today I will talk about stresses due to bending moments. So, new topic, stresses due to bending moment. If we have, for example, one beam this beam is subjected to the bending moment, pure bending moment in both sides, something like this. For example, this is beam, part of the beam. We apply bending moment in both ends. It will deform like this, you see. Initially it is a straight beam. If we apply bending moment, it will bend like this. Under beam we will have tension, you see, from the deformation. And top side of the beam we will have compression. So if we apply bending moment to this beam, let's see what will happen. Assume it is in two dimensions. This is x direction, y direction, and z direction it is perpendicular to the board and it is outward, or it is like this, z direction. If I assume one cross section for this beam, cross section can have any shape, but assume it is symmetrical respect to y-axis. So this is y, this is z. So assume the cross section it is symmetrical respect to y-axis. And here I assume it is rectangular shape. The width is b. The height I assume it is h. So here in cross section, x-axis will be perpendicular to the board and it will be outward. Now, if we assume a small segment of the beam, we assume a small segment of the beam, the length for this segment, assume it is delta x. The length for segment it is delta x. After we apply these bending moments, this will deform, and it will deform. Initially it is straight. After deformation, it will be something like this. So these two sides plane perpendicular to the beam will remain plane, but they will rotate, they will tilt. So the beam is bent and the sides of segment tilt. And the segment deforms into one sector. And for example, the radius of curvature for this sector it is rho, and this angle, assume it is delta theta. Initially the length was delta x. Then we will have curve shape. Initially it is straight beam, then we will have curve shape. And you see, beam is bent and the sides of segment tilt. Side of this segment tilt. And this angle of the curvature, we will assume it is delta theta. If you look at to the segment, what you see? Top side here and here, we have compressive strain. You see in top side, the length will decrease, it will contract top side. But we will have elongation, expansion in bottom side of the beam. So here we will have tensile strain, top side we will have compressive strain. So top side we will have a compressive strain, and here we will have tensile strain. But there is one fiber. Above that fiber, we will have compressive strain, and below that fiber, we will have tensile strain. You see, compressive strain will cause compressive stress, and tensile strain will cause tensile stress. There is a fiber. In that fiber, we don't see any deformation, or before we apply the bending moment and after we apply the bending moment, the length is constant. We don't have any deformation in that fiber. Above that fiber, we have compressive strain. Below that fiber, we have tensile strain. And it reaches to the maximum value on top and on bottom. So we have maximum compressive strain on top. We have maximum tensile strain in bottom of the beam. In this fiber, strain is equal to 0, and deformation is equal to 0, and stress is equal to 0. We will call that fiber neutral axis location. So we will call it neutral axis. In neutral axis location, for example, if it is rectangular shape, it passes from here, and above that it is h over 2, below that it is h over 2. This axis will pass through the centroid of the cross section. Why we will prove that? That this neutral axis will pass through the centroid of the cross section. In neutral axis location, strain is equal to 0. We don't have any kind of deformation. We don't have contraction, or we don't have expansion. And strain is equal to 0 and stress is equal to 0. But if beam is subjected to positive moment, it means underneath we have tension like this. In that case, above that neutral axis, we will have compressive strain, and below that we have tensile strain. Let's see what will happen if we assume somewhere we will have neutral axis, and we don't know the location of neutral axis. Assume we don't know. From top we assume it is, for example, C1. From bottom it is C2. So we don't know the location, but there is a one fiber. Above that we have compressive strain, below that we have tensile strain. See what will happen. I will draw this picture one more time, a little bit bigger. So beam after deformation will deform something like this. This is center of curvature. This is radius of curvature, rho, and this is neutral axis location. Above that we have compressive strain, below that we have tensile strain. From neutral axe to the extreme top fiber, I call it C1, the distance. To another extreme fiber, I will call the distance is equal to C2. I assume another fiber. This fiber distance from neutral axe, it varies, and I call it y. The distance, I call it y. This angle, we assume it is delta theta, and this black dashed line, I assume it is neutral axis location. Initially, the length of this beam, this segment of the beam was delta x. Initially, the length was delta x. I can write because deformation is small deformation. Because deformation is a small deformation, this angle is very small. So delta x will be equal to rho delta theta y. Initially, before deformation, the segment length was delta x. After deformation, above this neutral axis, we have compressive strain. Below that, we have tensile strain. But in the location of this axis, we don't have any deformation. So if before deformation the length was equal to delta x, after deformation will remain equal to delta x again. This arc length will be equal to, in the range of small deformation, delta theta times rho radius. Let's look at to this blue fiber length. What is the blue fiber length? Blue fiber length will be equal to, if I show that, for example, assume I show with, this is delta x, this is delta x2. It will be equal to rho minus y times delta theta y. From center to here, from center to the location of this blue dashed line, it is rho minus y, because from here to neutral axis it is y. So the length for this arc, blue arc, will be rho minus y, the radius, times delta theta. Let's see now what is the strain for this blue fiber. The strain for that fiber will be equal to the length after deformation, rho minus y delta theta, minus initial length. Once this beam was straight, these two fiber length, they were equal. So the length for even this blue fiber, in that time it was rho delta theta, or it was equal to delta x, divided by initial length. It was the length for this segment, that segment, and it is rho delta theta. From here, if I simplify this, I will end up with minus y over rho. So I can write epsilon, and because this epsilon, it is in the x direction, epsilon x is equal to minus y over rho. You see it is compressive strain because it is negative. So above the neutral axis location we have compressive strain. If we assume this blue line below this neutral axis location, in that case, because y will be negative 2, negative will be positive, and in that case epsilon x will be y over rho, which is, we call it tensile strain. So let's see what is happening above this neutral axis location. What is happening over there? If I look at to the cross section of this, assume the cross section is rectangular shape. This is the location of neutral axis. C1, C2, and the location of that blue that dashed line in cross section will be something like this. And this distance, it is y. If the thickness of this is dy times b, the width of the beam, will be area for this. I call that dA. So dA will be equal to b dy. I have strain in this fiber. Strain in this fiber times Young modulus will give us stress in this fiber. So stress in that fiber will be equal to, because sigma x is equal to E epsilon x, normal stress will be equal to minus E y over rho. So in the location of this fiber, I show with blue here in the side view, here in the cross section. Stress over there, it is negative E times y over rho. Stress over there. Stress times area will give us force. The force over there, so the force over there, dF, will be equal to stress, which is sigma x times dA. Sigma x is equal to negative dy over rho dA. So force perpendicular to this, fiber, it will be Ey over rho dA. If I show the side view of this, side view, it is initial location of the cross section like this. After deformation, it will rotate respect to neutral axis location. From here to here, it is C1, and this is C2. Strain distribution, above this it is compressive strain, below that it is tensile strain. So because strain times Young modulus, it is stress, here we will have compressive stress, and here we will have tensile stress. This blue fiber here, for example, the location from neutral axis, it is y, the thickness is dy. In cross section we will see like this. So stress here, sigma x times this dA, will give us force dF, force effective on that element dy F. If I integrate that force in entire cross-section area, means summation of forces in x direction. So summation of forces in x direction is equal to 0. That will be integration of this. We have several df in entire cross section, infinite number of df. If we add all together, it means summation of all those infinite numbers. It will be integration of df in entire cross section is equal to 0. If I integrate this in entire cross section, this will be integration of E, Y, rho, dA, and we have negative is equal to 0. E over rho, it is constant, so we can pull out of integration. I can write E over rho negative Y dA is equal to 0. E over rho, it is constant number. In order this times the integration y ds is equal to 0, this term should be equal to 0. So integration of y dA should be equal to 0. Integration y dA is equal to 0. Integration of y dA is equal to 0. If you remember how we find the centroid for one cross section, in order to find centroid for one cross section, we should calculate moment of area for that section divided by area. So moment of area divided by area, or I can write like this: y bar is equal to 1 over A entire area. Moment of area is y dA. So using this formula in static, if you remember, we used to find centroid location. So here y A is equal to integration of y dA, that is equal to 0. So moment of area respect to that axis passes through the centroid is equal to 0. Moment of area respect to the axis passes through the centroid is equal to 0. This is the definition of the centroid location. So from here we can understand the location of neutral axis is in the centroid of the cross section. So if this is rectangular cross section and entire height is h, C1 should be h over 2 and C2 should be h over 2. If it is not rectangular, for example, if it is trapezoid shape, again neutral axis will pass through the centroid and we should find the centroid location, and we can find C1 and C2. So neutral axis will pass from centroid of the cross section, and we can prove that with summation of forces equal to 0 in horizontal direction for cross section. Let's come back to this cross section one more time. We know now force in this fiber dF is equal to stress over there sigma x times dA, and sigma x is equal negative E y over rho times dA. It gives us force in this fiber, or force in this fiber. If we take moment respect to neutral axis location here, what we will have? We will have moment dm is equal to df times y. dF times y, if external moment, it is in this direction positive, this dF times y, it will be in inverse direction, so it will be negative. From here, dm will be equal to, instead of df, I plug this, minus and minus will create positive, will be ey over rho dAy. If I integrate this dm for entire cross section, I will end up with moment. Moment is equal to, internal moment is equal to E y squared over rho dA. From here I can pull E over rho out of integration because it is constant number. E over rho is equal to integration of y squared dA in entire cross section A. Integration of y squared dA, we know that. What is that? If you remember in static, integration of y squared dA, we call it moment of inertia. Moment of inertia. We will call it moment of inertia or second moment of area. We have moment of area. We use moment of area in order to find centroid location. Then we have second moment of area or moment of inertia. If you remember, we used to show with I. This is moment of inertia for that cross section. Respect to this axis passes from centroid. For example, here it is Z, it will be IZ. From here, I can write M is equal to E over rho times I. If I rewrite this one more time, I will end up with what? I will end up with moment is equal to EI over rho. Or I can write this 1 over rho is equal to M moment divided by EI. This is very important formula we will use a lot, so you should know it. 1 over rho. Rho is radius of curvature. 1 over rho we will call it in math curvature. Curvature is equal to moment divided by Young modulus times moment of inertia. I remove this. So we found 1 over rho is equal to M over EI. On the other hand, we find, if you remember, epsilon x is equal to minus EY over rho. From here, I can write 1 over rho is equal to negative sigma x over EY. 1 over rho is equal M over EI. 1 over rho is equal negative sigma x over EY. If I put these two equals, because you see the left side it is 1 over rho, I can put those equal. I can write M over EI is equal to negative sigma x over EY. From here, from both sides, E, they will cancel each other, and I can write sigma x is equal to negative, let's see, I had here, yes, I can write sigma x is equal to negative m y over I. This is very important formula. Sigma x is equal to negative m y over I. If m is positive moment will cause tension underneath of the beam like this. Okay? So if it is positive moment, y, the location of fiber above neutral axis location, divided by I is moment of inertia. You see, above the neutral axis, we will have compressive stress because it is negative. Below that, because y is negative, negative times negative will be positive. Sigma x will be positive. We will have tensile stress. So, stress is due to bending moments is equal to bending moment times y, the distance of fiber from neutral axis location, divided by I, moment of inertia, respect to neutral axis location, and neutral axis will pass from centroid of the cross section. So now if I remove all these, what I found, 1 over rho is equal to m over EI, and sigma x is equal to my over I. So sigma x, normal stress due to bending moment, is equal to bending moment times the distance of fiber from neutral axis location divided by moment of inertia. These two formulas are very important. We should know that, and we should know how we can end up with these formulas. On the other hand, from math, we know for one curve, 1 over rho, we call it curvature. And if we have one curve, the function for that curve, for example, y is equal to fx. In order to find the curvature for that curve, curvature is equal to second derivative of y respect to the x divided by 1 plus first derivative of y over x squared to the power of 3 over 2. We can prove this. We had this in calculus, so we know that. Now, we know curvature is equal m over EI. If we have one beam, initially beam is a straight line. After we apply moment, it will deform, and this will be curve after deformation. Initially it is a straight line. After deformation, the shape, it is similar to one curve. It is curved, not similar to the curve. It is curved shape. So for this curve, we can find the curvature. Curvature will be, if I define this curve function, y is equal to fx, it will be second derivative of y respect to the x divided by 1 plus first derivative of y respect to x squared, all to the power of 3 over 2. dy over dx for one curve, if the curve function it is y is equal to fx, dy over dx means the slope of that curve. So this term dy over dx, it is slope for this curve after deformation. So initially it is a straight line and slope is equal to 0. After deformation it is curve shape, and the slope for this curve, it is dy over dx. In math, in order to find the slope for one curve, we know slope is equal to dy over dx. We can prove that, and you know all those. Because here in mechanics of material, we are assume all material obeys Hooke's law. They are linear elastic material, and they are in the elastic range. It means deformation is very small. In a small deformation range, dy over dx, which is the slope of this deformed beam, will be very small. Very small quantity, square will be very small. So it will be close to the 0. So we can neglect this term. If I neglect that term, curvature 1 over rho will be equal to second derivative of y over x. So I can write here for beam in small deformation range. In small deformation range, material can behave linear elastic. I can write second derivative of y over x is equal to m over e r. This is very important. Later on I will solve example, you will see. Because if we want to find deformation for one beam, for example, we have simply supported beam. I apply bending moment here. This is A, this is B. For example, I want to find deflection in the middle of the beam. For example, or we have simply supported beam subjected to concentrated load at middle. It will deform. If we want to find maximum deflection or sagging of the beam, how we will find? We will find using this formula. I will explain that later on. I will solve example, but this is very important. So 3 formulas are very important this session. One of those, it is curvature 1 over rho. Rho is radius of curvature. 1 over rho, we call it curvature, is equal to bending moment divided by EI. E is Young modulus and I is moment of inertia. Normal stress due to bending moment. Normal stress due to bending moment in cross section is equal to bending moment times y, the distance of fiber. We want to find normal stress in that fiber. Divide up to neutral axis location divided by I, moment of inertia respect to the axis passes through the centroid. I can find sigma x. And second derivative of y respect to x is equal to bending moment divided by EI. For now, you should learn this formula, review this lecture 2-3 times, understand the concept. If you have questions, send me email. So after understanding everything, after you digest the material I covered this session, I will go forward and I will solve different examples. Thank you so much for watching this lecture. See you next session. Bye bye.